Good afternoon, everyone, and welcome to today's SANCOLD Young Persons Forum webinar. My name is Ashley Kutsia, and I have the pleasure of serving as the chair of the SANCOLD YPF. It is wonderful to have you all with us as we continue our mission of creating a platform for knowledge sharing, professional development, and technical exchange within the dam engineering and water resources community. Today's webinar is titled An Introduction to Hydropower, Foundations and Principles of Harnessing Water Energy. Hydropower remains one of the most reliable renewable energy sources available to us, and a deep understanding of its foundations is critical for engineers, scientists, and decision makers shaping Africa's water and energy future. This session will explore the core principles of hydropower engineering and the ways in which water can be harnessed to produce sustainable and clean energy. We are honored to be joined by two highly experienced hydropower specialists from Zutori, Reginald Barry and Rudolf van Beek. Today, they bring a wealth of expertise in hydropower projects across Africa and beyond, and we look forward to the insights they will share today. Reginald is a professional mechanical engineer with over 14 years of experience in hydropower, bulk water, and water treatment infrastructure. He has worked on project management, engineering design, commissioning, asset management, and the design and rehabilitation of hydropower schemes, pipelines, pump stations, and mechanical equipment, including advanced methods such as finite element analysis. He has a strong interest in digital engineering solutions to modernize and streamline design processes. His project experience spans Southern, Western, and Eastern Africa, as well as work in New Zealand and Australia, giving him broad international exposure to water and energy infrastructure challenges. Rudolf is a design engineer at Zutori with over 30 years of engineering and technical management experience. He has managed numerous hydropower projects and served as lead electromechanical engineer on several major designs. His expertise includes pre-feasibility and feasibility studies, EPC bid and detailed designs, as well as site inspections on hydropower and dam hydromechanical projects across Africa. He currently leads the hydromechanical section in Zutori's dam and hydropower unit, acting as project manager and lead engineer on multiple assignments. His professional experience spans projects across Southern, Eastern, and Western Africa. Before we begin, I just want to remind you that this session is being recorded and will be made available within the next week. Your microphones and videos have been disabled to minimize background noise, so you can use the chat to post any questions or comments that you have during the session, and we will address them during the question and answer session after the presentation. And with that, it is my pleasure to hand over to our speakers, Reginald and Rudolf. The floor is yours.
Thank you very much, Ashley. Thanks for the very kind introduction. Ashley, please just indicate if you can see my screen.
Yes, you're audible and visible. Thank you.
Okay, very good. All right, thanks everybody. Thanks colleagues also in the industry. I know many of you on the call here work with Rudolf and myself also on a daily basis. You're also, professionals and engineers in the industry, either full-time in hydropower or part-time, partly rather. So yeah, thanks for making time to join us for this. I think we have a long way to go with hydropower in Africa specifically, but also South Africa. And there's an enormous potential across our continent for hydropower, also globally, but specifically in Africa. And I think if you're not excited yet, hopefully this session will excite you even more. Hydropower is a fantastic renewable energy source. And yeah, I think hopefully enjoy this session. So I'm going to turn off camera and then go on into the first slide. Okay, so just a little bit of an overview. So what is hydropower? I think the important first note here is that it is renewable energy. And we'll dive into that in more detail. about why it is renewable and also how does it compare with other renewable energy sources. It's derived from moving water, water that flows in a river, for example, or that you pass through a conveyance system, which we'll discuss in more detail. It converts potential and kinetic energy of the water into electricity, and it's actually one of the oldest and most widely used renewable sources. You can think back to the water wheel. Sure, most of you have seen water wheels in action, and yeah, so turning a water wheel and turning that into electricity. It's been around with us for very long. And I think that whilst there are many very exciting developments in hydropower, also in recent years, the fundamentals essentially stay the same. And we'll touch on that a little bit. Key principles. So, in terms of potential energy, it takes water that's stored at a certain height. So either in a reservoir or a dam, or a river, and then where there's a flow in the river, but call it a rapid, so a drop in elevation. There's obviously potential energy, and that you can convert into electricity, and the same for kinetic energy. The conversion process is actually quite basic. You take water, you pass it through a turbine. The turbine spins the generator, and that turns all of that energy into electricity. You take it through a transformer and an overhead line, and you connect it to the grid. So, as I said, very basic principles, nothing rocket science. I think what makes hydropower so exciting and interesting is how hydropower comes together through so many different engineering disciplines. Now, why hydropower over maybe some other sources? It's a very reliable source of energy, and it's flexible. And they've got a slide on that to go into a bit more detail. But if you build a hydropower plant today, it will last you a very long time. 25 years for electromechanical, hydromechanical, and electrical equipment, and it will continue for many years thereafter if you construct, design, and construct it well, and if you operate and maintain it appropriately. A hydropower plant can even get you to 100 years and more, of which there are also several across the world. Hydropower is fantastic actually in that it supports grid stability. So either in base load generation mode or for peak generation. You can use hydropower for both of those, whereas with wind and solar, it's obviously a bit different. Touch on that in another slide. In general, it actually has very low operating costs. As I said, you've got long asset lifespans. Hydropower can last you very long, and in those years, as I said, if you design and construct it well, and you give due consideration to environmental factors and things like that, that you protect the plant, then it can last you a very long time at very low costs. And then I think very important here is that it contributes to energy security. In fact, many African countries rely to a very large extent on hydropower. We've got several countries in East and Southern Africa that is heavily dependent on hydropower and in ensuring energy security for the population and the country to function and operate properly. And it also contributes to climate goals, because compare that, for example, to coal-fired power stations. Hydropower is pretty clean. It's quite an impact initially, or could be quite an impact initially when you construct it, because you typically have to inundate water. You have to temporarily alter a river course and things like that. But in the long run, and also you can mitigate those construction-related impacts. But in the long run, it's a clean energy source, so it contributes greatly to our climate goals that we as a as the population of every country actually has and need to take quite serious if we want our future generations come after us to also have their spot on Earth. Okay, so let's briefly touch on the global hydropower potential. We'll start here on the left. If you look at this line down here, This is from the International Hydropower Association's World Hydropower Outlook report or book that was released. It's released annually, and this is from the 2024 report that was released early this year. And you can see that in the global terms, only about 1,400 gigawatts have been exploited. So we're only generating about 1,400 gigawatts of hydropower. And if you add the pipeline, so the ongoing and current projects, it gets you to 1,700. That's only about half of the hydropower potential that is available globally. So we've got a long way to go. Even though hydropower has been around for hundreds of years, it's recently only been really tapped into to a mega scale. And if you look here on the right, you'll see that 24 gigawatts of capacity was added globally into 2024, inclusive of pump storage, and 189 gigawatt of capacity, pump storage capacity was installed up to end of 2024. So there's a massive potential in the world. And in the next slide, we'll go into a bit more detail on Africa specifically, which should be really exciting to all of us on this call, assuming that everybody is from the African continent, because there's fantastic job opportunities, career opportunities in hydropower. Now, just to bring all of this a little bit into perspective, South Africa's total installed generation capacity, so if you think Eskom and the grid and some IPPs, private producers that generate power, if you add all of that in, we've only got about 55 gigawatts. So not all of it is available, but that's our installed capacity. And of that, only about 3.5 gigawatt is hydro in total, but 2.9 gigawatt of that is actually pump storage. So we've got 4 large pump storage schemes in South Africa, and those 4 add up to the 2.9 gigawatt. South Africa has got quite seasonal rainflow, which is why most hydropower, run-of-river hydropower schemes in Africa sits further north, of South Africa. So typically around the equator and also in West Africa. We just have our rainfall is just too seasonal. So you build a hydropower scheme, you start it up in the wet season, you get really good generation and flow, but then you don't have flow in the dry months, and then you really don't recover any, of your installed cost, your capital cost. So yeah, most hydropower plants in countries or areas, and not all countries are, or the rainfall is not constant throughout countries. So it's specifically to areas that have catchments that are that have quite constant rainfall or rainflow and stream flow throughout the year, so that you have consistency in stream flow and that you can generate throughout the year. Okay, so moving on to just a map that shows Africa specifically. If you look at the key here on the right, the remaining potential in Africa is 487 gigawatts. Now that's more than any other continent, and compare that to the current installed hydropower capacity of 43 gigawatt. In the years to come, all countries and continents around the world that is interested and invested in hydropower, and we can see that already happening, is going to put their eyes and their focus on Africa, because there's so much potential, and not just the potential, but if you look at the demand and the current available power in Africa, there's a massive potential to expand. There are challenges, obviously, in Africa. Some countries don't have the necessary network or transmission infrastructure. For example, security in some countries are typically a concern, but the people, the population is there. The need, even though many people in many countries don't yet know it, the need for electricity is enormous. And if we can tap into that hydropower potential, we can improve the livelihood of people. We can provide energy to cities and villages and towns. And because the potential is there, we have to tap into that. We have to help create the transmission infrastructure, the power back generation infrastructure, so that we can, grow Africa as a continent. Okay, moving on. Maybe something to note. Just compare that with Europe, for example. The potential in Europe is largely being exploited. There are some new projects, quite a few pump storage schemes popping up in Europe because of all the solar and wind that have been implemented, so variable renewable sources. And so pump storage hydro is the hot topic, I would say. In France, in Paris, just last week was the International Forum on Pump Storage. So there's a lot of focus, emphasis on pump storage across Europe. I recall the outage that happened across Europe, Portugal, and Spain last year. And that's largely due to variability and stability issues in the grid. So pump storage is a big thing in Europe, but most of the other run-of-river hydropower sites have been tapped into. But yeah, in Africa, it's very exciting for us. So if you're not yet in hydro, really consider steering into hydropower. Okay, so we talked about the untapped potential and the 487 gigawatt remaining potential in Africa. Now, major hydropower regions with development opportunities include the Congo River Basin, the Nile, and the Zambezi. That's only some of the major ones. Then there are, in many countries, there are the local or regional catchments that have very good rainfall throughout the year. And that's obviously what you want, so that you can continue to generate every month of the year and with not much variability. The DRC, Zambia, Ethiopia, Cameroon, Mozambique, Angola, Tanzania, Kenya, all of these countries are on the hot topic list, if you can say that. In Africa, there's many hydropower developments in each of these countries, and still a lot of potential. You'll see there are 4 key developments that actually happened in 2024. Very exciting projects. Take some time, go on the internet and read about some of these projects. A major one just recently launched or opened was the Grand Ethiopian Renaissance Dam, where 800 megawatt was added. And then Naktikal Hydro in Cameroon. So there was quite a big presentation of the Cameroon project in the end of last year at a hydropower conference in Africa. So very exciting projects for these countries. All of these countries desperately need more generation. And so these are some big projects that are happening around us. Very exciting. Okay, in terms of grid integration, so this is not a slide to go into the technical side of grid integration and how we keep our networks and grids stable. That could be several webinars on its own. But if you look at solar and wind, these are called variable renewable energy sources. So that means if the sun doesn't shine, then there's no power obviously generated, and same with the wind. So you kind of have to, if you want to rely only on solar and wind in a country like, let's say South Africa, you kind of have to have enough of wind and solar generation facilities in enough places, so that when the sun doesn't shine in one part, and I'm talking through the day, or the wind doesn't blow, that you have other facilities in other parts of the country that all contribute to the grid. But even if you do that, you're still going to really struggle to keep a grid stable. And after 5, 6 in a day, when the sun starts going down, you lose all of that generation capacity. So the two combined, sun and wind, it could be a good match. But even then, we've got peak hours in the morning and we've got peak hours in the afternoon, and you go home after work and you want to cook some food, and you want to heat up your water for showering and bathing and that sort of stuff. And those are our peak hours. And so to get through the day, Eskom and other utility companies, they've got to balance their energy sources, energy generation facilities, so that they can meet the demand in peak hours of the day. And so for that, typically with solar and wind, you need storage. So either battery, so battery energy storage system, BESS, or you need hydro. That's actually what we say you need. So you need hydropower facilities, specifically pump storage, for peak load. But for base load, you can rely on run-of-river. In a country like South Africa, that's challenging, as I said, because we don't have we've got seasonal variability, so it becomes a bit more challenging from baseload point of view. But we have many facilities, hydropower run-of-river facilities in South Africa that do contribute to the baseload generation. But then we also use our 4 pump storage schemes in South Africa. And actually, if you remember load shedding, which thank goodness is behind us for now and hopefully forever, the pump storage schemes in South Africa, in Gula, Drakensberg, Comet, and Steenbras, those were used extensively during load shedding to provide power during the peak hours of the day, essentially. So hydropower is nice in that it's got a spinning reserve. So you've got inertia in these machines that help you to act quickly to changes in the network. So it's got a fast response time. You can use it to help regulate the frequency in the grid, which in South Africa is 50 hertz. It provides you storage. So obviously, if you build a dam, then you can have storage, and you can actually hold back the water and release less during the daytime, and you can release more during peak morning and peak afternoon periods. And it also has black start capabilities. So our pump storage schemes in South Africa definitely permit, not sure of all of them, not sure about Steenbras, no, but the other 2 do, is black start capability, which means that if for whatever reason we lose the grid completely, like what happened in Europe or parts of the grid, then we can use these facilities to re-energize and start up the grid from scratch, essentially. Also voltage regulation. So as your demand changes, one person switches on a kettle and another one turns it off, and 3 more other people turn on their heaters. All of those things, and this is at a micro level, but all changes, all in the grid, all demand changes have an impact on the frequency and the voltage in the network. And we've got very tight tolerances that we have to maintain the network at, to make sure that equipment in commercial, residential, industrial facilities are protected, and that we keep the grid stable and safe. And so hydropower can help to regulate the voltage in the network. Okay, moving on. So the basic principles, and really this is hydropower. If you understand this formula, then you are already a hydropower engineer. So it's really very basic. Power, that you want to generate in kilowatts or watts, megawatts, is really a function of flow and head. So you need flow, Q dot. You need flow in a river, or from a top dam to a lower dam through a conveyance system. And you need a difference in head. You could have like just the kinetic energy of water flowing, like what they have in tidal facilities. But that's then you use a velocity head, moving water to generate power, but those are watts and small low kilowatt ranges. So for large hydropower facilities, you need head and flow. That's as simple as that. If you've got flow and you've got head, then you can play around with the efficiency of the scheme. And so important to note that this head is head after losses. So it's not just the difference in elevation between the intake or the upper dam and the lower dam. It is also inclusive of all losses. So you are going to have losses in your scheme. You're going to have your friction losses and minor losses. Friction losses through the conveyance system, minor losses, intake gates, entries and exit losses, all of those sort of things. And if you take all of those losses and you take it off from the static or grass head, then then you have your net head, and the net head times the flow in this formula is how you calculate your power. So really very basic engineering 101. You got, in terms of head, if you classify or compare hydropower facilities in terms of head, you've got high head plants and low head plants. I guess you can sneak in medium head plants in here, but typically we refer to high head and low head. So let's take a bit of time and just talk through these types of hydropower plants. So high head on the left, you've got a reservoir or with a dam. Could be just a weir or a spillway, a diversion weir. They've got a river, say, up on the mountain, and that river drops through along the mountain. It drops significantly down to the lower part of the river at the bottom of the mountain. So in that scenario, you could build a diversion weir at the top. You can inundate the water, and you can divert it into an intake, which is typically up here, and then into a canal, or it could be a low pressure tunnel. It could be a pipeline, and then into a valve house. So before you go into the penstock or high pressure pipeline, you take it through a valve house where you control the flow, and then into the penstock, and then down high pressure. As you go down to the powerhouse, the pressure increases more and more. And then in the power station, you take it into a turbine. Turbine drives the generator output terminals feed switchgear, and then into step-up transformers typically, and onto the network or the distribution line. So that's a typical high plant. Because of very high pressure and flowing water in the penstock, if you suddenly shut down the turbine in the power station, or it trips rather from an electrical fault or network outage, then you typically have a back pressure or a wave, a transient wave in the penstock that goes through the powerhouse, through the valve house, and then you need a surge tank to deal with that. The surge tank could be along the penstock, or in this case, the surge tank is for the low pressure tunnel to also deal with surge waves, hydraulic transients in the pressure tunnel itself. Okay, so that's the basics of a high head plant. A low head plant on the other side, on the right hand side, is where you typically do run of river, where there's not much head difference between where you take the water in on this side and where you release it. This could be say, river with a diversion weir or a dam, which you then pass through again. Typical, low pressure canal and a penstock, but in this case, what you see is more of it's a dam with a powerhouse almost integrated into the dam. Is separated here, but the powerhouse itself could also be integrated, tied into the dam, and form part of the dam construction or the weir construction itself. So this low head plant here, you've got an intake, typically with some screens, so coarse or fine screens that take out any debris that comes down. You can have the same, obviously, on a high head plant, and you typically do have. On a high head plant, it's quite important. We've got a high head, you typically have Francis and Pelton turbines. So you need to protect the turbines, and so you need to take out debris that is larger than what the turbines can handle. On the low head plant, these are typically your Kaplan and propeller turbines. So you've got a bit more solids handling capacity, but even so, it's still the same concept applies. So you typically have intake screens, then you pass the water into head race or penstock, and then into the powerhouse turbine, and then out on the other side through the tail race. Yeah, so some hydromechanical equipment that you see here are radial gates, for example. So on a dam, if you have a spillway, the spillway could be a gated spillway, where you use gates such as radial gates to control excess flow. So if there's a flood event and you get very high volumes of water coming down the river, you've got to pass that safely. The powerhouse still continues to operate, but you've got to deal with large flow. So you typically have radial gates. So any hydropower facility is actually a very good combination of civil works, as you can see. So you can make your career in civil engineering, in hydro as well, You can design dams, you can design canals, you can design structures, powerhouse or valve houses, intakes. There's so many things you can do in civil, but it combines civil with hydromechanical and electromechanical. So your screens, your gates, your stop logs, all of those things are your hydromechanical equipment. So all of these things really come together in hydropower. So it's a very diverse field of engineering. If you like working with other engineering disciplines, it's a fantastic way um, to get exposure to that. Okay, moving on. Then on the left-hand side, you see a typical run-of-river scheme. This is the part of the Gigi Molembwe scheme in Burundi. It's two plants, combined 49 megawatts. These two plants almost double the available power in Burundi. And on the right-hand side, you see a typical reservoir hydropower plant. This is called the Kashimbila Hydropower Station in Nigeria. And this is what I referred to earlier, where the hydropower station is integrated into the dam spillway. On the left-hand side here, you can see there's the weir itself. It's a PK Painoki weir, and then into the intake. And then something we haven't touched on yet, I haven't touched on, is the desander before it goes into the low pressure pipeline. So yeah, we can call it a desander or a desalting chamber or structure. So that's when you have a lot of sediment and siltation in the river coming down into the dam, where you also have to take that out of the system before you pass it into the pipeline, the conveyance system, and that is really to protect the turbines from damage. So you can imagine if you have high pressure, specifically high pressure water that passes through a Pelton turbine, or Francis, you can badly damage the runner of the turbine if you have a lot of sand and sediment in the water. So yeah, two typical examples. Now, types of turbines, I've mentioned some of these. On the top left, you've got a Pelton turbine. This is a horizontal Pelton because the shaft is in the horizontal direction. The shaft goes into the page here. So you've got water from your penstock or pipeline. It goes through a jet or a nozzle, and then that water jet passes on to buckets in the Pelton, and that turns the Pelton wheel, which is very similar to water wheels in the old days, but it's very high pressure. Pelton turbines are typically used at very high pressure applications, and then that turns the shaft, and the generator is connected on the other side of the Pelton. And then on the bottom left, you've got a Francis turbine. So that's the runner in red that you see here. So you've got flow coming in radially and then passing through the turbine runner. And that turns the main shaft, and the main shaft turns the generator. So this is just a typical vertical Francis with a shaft in the vertical direction. You can also tip it on the side. You get vertical and horizontal Francis turbines. Then on the top right, which we have many offers in South Africa and in Africa as well, is your low head Kaplan and propeller installations. And there are, again, many configurations. This is called the S type. So you've got a shaft that goes through the draft tube with a bearing house here. And that shaft goes into the runner itself. And you can have the runner in a Kaplan, the guide vanes, and the runner blades, they can turn, and so you can control, regulate the flow. And so that this is a typical S-type Kaplan turbine installation, and that goes then into often a gearbox and then a generator. So the gearbox is used to then change the speed between the turbine shaft and the generator shaft. That's a classic Kaplan installation. And then on the bottom right here, you've got a crossflow turbine. So it's a cylindrical runner. As you can see, that's a runner here. And these are quite common in between low and medium. So sometimes the Kaplan doesn't work that well. You're sort of heading into the higher heads and not a perfect match or fit for a Kaplan. But you're also not quite where Francis is. So instead of putting variable speed drive on Francis turbines and things like that, you could go for cross-flow turbine. All of these turbines could have very high efficiencies if you select them appropriately and if they are a good fit for the flow and head range that you have. They could all be very efficient turbines. Okay, just moving on to this graph here. There are, if you Google, you'll find hundreds of these graphs, all slightly different, but it's a very typical graph of where each turbine would fit in. So Kaplan and propeller is on the low head side. You can see they overlap as well. So depending on the flow, you could still have a Kaplan on higher heads, and same with Francis. But yeah, there's a typical range here of where you would use each turbine, but it's very specific to each project and to each site, water quality, and many other factors that you have to consider in selecting the most appropriate turbine. There are also many manufacturers, so original equipment manufacturers and turbine generator manufacturers across the world. Some of the key names are GE, Andritz, Voith. Yeah, there's many, but all of these manufacturers, they all have their own unique designs. They all have created their own patents. And so if you go to 3 different suppliers, you may also find that this graph looks different for each supplier. But it's a good starting point. And if you do a hydropower project, you would have sort of eyeball it from a graph such as this. And then you would reach out. Typically, you can use literature and there's good textbooks on hydropower, but you would typically reach out to suppliers to see what they can offer and how they can customize their solutions. This is particularly true in pump storage schemes where you have Francis reversible pump turbines. So essentially Francis, such as you see here, but where you can pass water through it to generate power, and you can also turn it around. You can pump with that same machine, and Rudolf will touch on pump storage schemes a bit later. Okay, moving on then to typical scheme components. We've touched on this in the previous few slides, but I think this is quite a nice picture. So you've got your diversion weir, dam, reservoir up at the top right. Then you've got an intake for the hydropower conveyance scheme, the desalting tank, and then you've got what is called the head race. So the head race is between the intake and the forebay, and that head race could really be anything from a canal pipe to a tunnel. It depends on the topography. It depends on material availability. It depends on hydraulics. So there's many factors that you have to consider in selecting the most appropriate head race. It obviously also depends on the drop in elevation between the intake and the forebay. If you have a significant drop in elevation and you have to live with it, call it, then obviously a canal you would struggle with. You could then go for a low pressure pipeline. But that's just one of many factors that you would consider. Then you've got from the forebay, you've got another intake here into the penstock. And typically at the forebay, you would also have what is called a reject weir or a reject conveyance facility. So if the powerhouse turns off, trips, if the turbine's tripped, then you obviously have water coming to a standstill in the penstock. And so that transient or pressure wave would go back into the forebay, so the water level would also come to a standstill in the head race, and that then creates a backwater wave in the head race, and then you have rising water levels. So quite often from the forebay, you would have a reject weir to then essentially spill that water back into a channel that flows back to the river. But this is a typical installation or a typical layout rather. And then from the forebay, you typically have an isolation valve at the top of the penstock. So that is, to isolate the penstock itself, so prevent any water from going into the penstock, also to drain it for maintenance and operation purposes. And then through the penstock, it could be an above ground or a below ground, a trenched penstock pipeline. So that penstock then goes down into the powerhouse, where it typically bifurcates into a manifold so that you can feed multiple turbine units. If you have only a single turbine, then obviously the bed stock would be going straight into the turbine. Okay, then in the powerhouse, that's also probably a webinar on its own, but you have a generator and a turbine, and then you've got lots of electrical control and protection systems. So if you're an electrical engineer, electronic engineer, and you love switchgear, control and protection systems, panels, transformers, step up transformers, and substations, then there's a very nice and interesting career opportunity there. So then from the generator, your generator then feeds the generated electricity through the electrical control and protection systems. You typically have a switch yard or a substation at the plant where you step up from the voltage of the generator. You step up to a higher voltage so that you can then connect to a distribution or a transmission network. The line could be private, or it could be part of the utility company's network. Yeah. So and then the tail race is just where you release the water that went through the turbines back into. So it's obviously a non-consumptive system largely. The water that comes into the diversion weir, it just passes through the system. Use the energy in the water, you drive the turbine, and you pass the water back into the river. So largely, it is a non-consumptive scheme or system. And we talked about hydromechanical equipment there with gates, stop blocks, valves, pipes, bed stock, all of these things. Okay. Then moving on to plant viability. So if you need to decide whether a specific hydropower site is viable, if you can build a hydropower plant there that you can operate and you can commission and you can generate revenue from, and you can recover the initial upfront capital costs and the ongoing operational costs. There's many factors that you have to consider. So on the energy yield side, the energy yield meaning how much gigawatt or megawatt hours can you generate using this facility. So we typically use the flow data, available flow data in a river system, and that could be through gauging stations or other means that you determine the available stream flow. And then that available stream flow you put into what is called the flow duration curve, which is this red line that you see going down here. So then on this graph, the exceedance is shown on the x-axis here, down here, and then the flow is on the y-axis. So what this means is that at any given point on this graph, let's take that point, if you take that down, means 25% of the time you will get that flow. And if you take another point here, so off the page 10%, so 10% of the time you would get the higher flow. So it makes sense, right? You have most of the time you have your lower flows, and less of the time you start getting into this range where you have lower flows in the river. So you draw up this flow duration curve, and then you decide for which range do you want to size the turbines and the scheme with all its conveyance systems. So if you want to target a very low flow here, sorry, very high flow but low exceedance, then you're going to build very large infrastructure to deal with the large flows, but you're only going to have those large flows for a short period of time, per annum, for example. So 10% exceedance would be typically 36.5 days out of a year. So we then look at this, and you say, okay, I'm going to size my turbine typically for 25 to 70, 80, 90, whatever. In this case, 85% exceedance, and then you use the flow data points along here to then calculate your energy yield. And so then you calculate from this your P50 or 50% exceedance probability, 90% exceedance probability, and 10%. And you use that in your financial model so that you can stress test your financial model to say, okay, if I hit a dry year, then can I still make this scheme financially viable. If I hit a lot of wet years, it's obviously nice, but you have to look at variability. So you stress test your financial model. And so seasonality, outages, energy losses, all of those things gets added to the energy yield. So you look at flow and head, but then to really look at energy yield, you need to add things like seasonality, outages, and energy losses. Okay, then you can look at peaking operations. So in other words, you don't just take what comes into the river, you either inundate and store the water, and you release more in certain times of the day, and that's peaking operation. And then you start going to the commercial side of things, which is your power purchase agreement, your PPAs. And there's many factors within the PPA that will have an influence on the financial viability. So there we think tariffs, ancillary services. So what we talked about earlier is voltage and frequency regulation and things like that. And also wheeling, where you generate the power as an independent power producer, and you pay Eskom transmission company, for example, a fee to convey that electricity across the network, but your off-taker is a private company, for example. So you essentially wheel through the network. So those are very important commercial factors to also consider in plant viability. And then obviously cost. So capital cost, your upfront cost to develop and construct the scheme. And then after it's been commissioned, you start with O&M, operational maintenance costs. And all of those gets thrown into a financial model, typically by clever chartered accountants or financial people. And then they assess, with things like interest rates on financing and stuff like that, they assess whether this plant is financially viable over a 20, 25, 30 plus year period. Okay, I think then over to Rudolf.
Okay, thank you, Reg. So obviously, as with any dam, any development, there are always risks. So the typical risk that you look at in a hydropower plant is first and foremost, always the hydrology. Water is the actual fuel. Water resource is the fuel of the hydropower plant. So you need to look at water availability, the seasonality that we've already highlighted in the presentation. A problem in South Africa in that our seasons, you have wet seasons and dry seasons, and then that obviously have an influence. And very important is climate resilience. What is going to be the impact of climate change on this plant? So you need to assess all of that and then determine what is the resource availability. Typically, the output of the hydrology is the flow duration curve, and that's where we then stress test whether a P90, P50, P90 being the dry years, P10 being the wetter years, and you put that into the system and you start understanding what's the energy potential, and there are certain risks then involved with the hydrology. Flooding is obviously a major issue. You're working on rivers and floods will occur, so you need to understand the flood risks and how you're going to handle those flood risks. Sediments, very important. Obviously, you need to be able to cater, well, if there's a high sediment load in the water, as previously shown, you need to have a desander of sorts to get rid of the sediment. Also, if there's going to be a high sediment load at the weir, you need to make sure that it doesn't clog up your intake. Similar debris, a lot of places up in Africa, well, everywhere, you have floating debris in the river, and large tree trunks coming down, maize leaves, etc. All those things, if they get stuck onto a turbine, obviously they can damage, they can clog it up. And then, as with any dam, and geotech, geology is quite key. There's always risk when you start designing the hydropower plant to understand those geotechnical aspects of it. And then topography, typically it's not a risk, but because you can these days have very good LiDAR surveys or surveys done, but at a very early stage, we're not sure about the available air. It is a risk. And then the water quality, once again, you need to understand the water quality of the water. if it is very corrosive, etc. And then a big issue is always the power evacuation. So is there grid capacity, and is it available to actually evacuate the power? A lot of places, specifically with solar and wind now being put up everywhere, there's not access to the grid because of that, and that constrains the grid. So you can generate, and the project is feasible, but now you need to construct a power line of hundreds of kilometers to get to a substation where you can connect into the grid. And then, as always, the environmental impacts are very important. You need to look at the terrestrial, the aquatic, and the avian impact of the plant on it. And very important is the environmental water release. As Reginald had previously shown, you divert some of the water, but you cannot starve the river between the power station and where you divert. You have to keep the aquatic system still going. So there's always an environmental water release from a weir to ensure that you don't starve the river. And then, as with any dam or any construction project, you need to look at the social impacts as well, which becomes the bigger the project, the more intense that problem becomes, specifically if you start building hydropower plants with huge reservoirs, etc. You can move on, Reg. Reginald? Yes.
You see
Okay, I'm just going.
I've moved on.
Okay, so yeah, this is just to show you an example, a more real life example of a hydropower plant that we've been working on. This is Nulubali on the White Nile in Jinja, Uganda, that you see there on the top left corner. So in the foreground here, you see the actual substation with all the power evacuation and the protection, etc., on the network side. Then you see the power station there, just at the back of the river, and then the actual dam that dams up Lake Victoria in this case, to the left there. At the bottom here is a drawing of the actual hydropower plant with the intake on the left-hand side, and then the water flowing through into the turbine with a section through the turbine. And these are double regulated Catlin turbines that you see there with the generator on top. And then a very important aspect when you start designing the hydropower plant is always that you need to be able to maintain it. So obviously you need to be able to take out the turbine, you need to be able to take out the generator. So there's an overhead crane there, and then all sorts of auxiliary systems within the powerhouse. On the right-hand top corner there, you just see a scan of the hydropower plant that was done so that you could actually use that in the design. We're looking at the rehabilitation of this hydropower plant at this stage. Then on the photo on the left-hand side, the very first photo there, on the right-hand side, you see people actually standing in the spiral casing where the water actually flows into the turbine. This is for one turbine where the water actually turns now into the turbine. And then you see the actual inlet gate at the back there. You can't see it clearly, but there's a gate. And this turbine specifically has a flow of 115 cubics per second. So that's a hell of a lot of water that flows through that turbine. In the middle photo there is the actual powerhouse with the overhead crane here in the foreground. And then the blue boxes that you see along there, those are the actual generators. So it just gives you an idea of the scale. This is a 180 megawatt plant. Then on the right-hand side, these are the guide vanes of actually the inlet into the turbine. So it's just to give you a more real-life example of what is involved in a hydropower plant. Okay, you can move on. Okay, so just a bit on pump storage and how pump storage plants work. So in essence, it's an energy storage device where you store energy at a high, well, water with a energy potential at a high level, and then you let the water run through a turbine into a lower reservoir, and obviously when you do that, you generate electricity and you put that back into the grid. And then you typically do that when either you require energy onto the grid or there's high tariffs available for generating electricity in South Africa. And then obviously you need to pump the water back when you have sufficient energy in the grid available and or the tariff is low. So we sort of become like a trading system, and the system typically then a pump as turbine that sits in the middle there. You also similar to the hydropower plants have problems with surge. So if you look at the underground power plant that sits in the middle there, you also have the low pressure pipeline coming in from the dam, but that also, if that pump stops, you have surge, so you need to have a surge tank there, and then also you will have surge, and you'll need to do a surge analysis on the actual penstock leading up to the upper reservoir if the turbine trips, etc. But in this case, the upper reservoir is actually being the actual surge chamber, so to speak. Then you also have the transformer yard, the switch yard, and the power evacuation. So, and then a very important aspect is specifically for pumped storage hydro plants. As you see on this screen, is that most of the stuff, well, the generation, the power plant is typically underground. You also get these powerhouses that's above ground or next to the lower reservoir, which has less excavation. So there's various variants of these options that you can consider, but then you need access into that powerhouse, and that is quite important, from a safety perspective, operational perspective, as well as from a construction perspective, and a little bit more about that later on. You can move on, Reg. So you can click the typical reservoir considerations that you need to look at for a pumped hydro storage plant is, first of all, you need to get the right type and height of the dam. So what you see here is the top and the lower reservoir all in one photo. So typically the top reservoir being on top of a mountain is typically a crow's nest type dam, such as this one, and then also in this case the lower reservoir is also got quite a long embankment there. So you need to do dam type selection. Obviously the cost of these embankments becomes quite huge, so there's different trade-offs, and then you need to look at the height of the dam. You also, obviously, like in any dam, you have the active storage and the dead storage that you need to consider. You have evaporation from the dam. Seepage is quite a key problem, specifically for both dams that you need to look at, because typically the top dam is mostly constructed on top of a mountain. So it's not in a river. So seepage is a huge problem that you need to look at, and then you need to look at the freeboard related to the actual reservoir as well. That's also now caused by the water pumping as well as the wind that you will have on top and at the bottom. And then a very important aspect would be the lining. So typically you would line the dams, because if you pump the water up, that's energy that you store in there, and you don't want that water now to dissipate into the surroundings. Obviously, there's an environmental constraint with that as well. Then you also have the inlet outlet works. You can carry on, Reg. And then the spillway is quite an important aspect related to this as well. depending on where your dam is located, sometimes the top dam does not necessarily have to have a spillway, depending on the catchment of water flowing into it. But there's always the issue that what happens if you have an overflow and where will the water go? And therefore, specifically for the top dam, but also then for the lower dam, the dam break analysis become quite an important aspect, as you have a huge volume of water sitting on top of the dam, obviously becoming quite a high risk. You need to look at the top-up of water, of the water resource, because of evaporation and seepage out of the system. And then instrumentation and control becomes quite an important aspect from a dam safety perspective, because if you start pumping or generating to the lower dam, how do you make sure that you don't overtop the dam? So you need to have very secure instruments, etc., in place to make sure that that doesn't happen. And then the construction and schedule of the dams becomes quite an important aspect as well, and similar to the cost. You can move on, Reg. Okay, so this slide is about the powerhouse, the underground powerhouse complex. That's, as I've said, sits mostly underground. As you can see in this example in the right-hand corner, it becomes quite a complicated underground tunnel system. First and foremost is to actually get the powerhouse complex constructed that you see in the right bottom corner, and you're actually starting at the top and then excavating down. So you need to have an access tunnel into that power complex, and then you start excavating, and then you need to get rid of all of that excavated material that needs to be trucked out. So your tunnels needs to be sized correctly accordingly. The underground powerhouse is typically on the critical path, and so, these projects, depending on the scale, you look in excess of from the moment that you press the button until you start generating, you're looking at anything between 6 to 10 years for construction because of the underground, and there's a lot of focus trying to optimize the timing for the underground stuff. In order to do that, you do a lot of geotechnical investigations, early access tunnels into the underground, so you can start measuring the rock characteristics and understanding what's happening with it. The ventilation becomes quite an important aspect, and then obviously you try to keep the slopes of the access tunnels not too steep, and then you're also looking at having conveyor belts to get rid of the material. And that is the presentation. The only next slide that I want to mention to you, for those of you that are interested in hydropower and want to find out more, we as SANCOLD is actually running together with the conference, the 2 days through before our conference, we're running a hydropower course that you can find out a bit more, the detail of that on our webpage. You can go to the SANCOLD and go to the events page, and you can get all the information there. And we'd be happy if you can join. There are basically 2 options. So obviously, the one option is the actual 2-day course, attending it's 2-day course, and it's 2,500 Rand per day. If you actually attend the course in person, you can also have an online option of 1,000 Rand per day, but then there are no CPD accreditation for that. And that's it. Thank you. Thank you for the opportunity for us to discuss with you hydropower. Thanks. Over to you, Ashley.
All right, thank you. I would like to open the floor to some questions. So if you have a question, please raise your hand. I will enable your mic, and then you can speak to our speakers, or else you can just write your question in the chat, and I will address it through there. I see we have a hand. Alan, I have enabled your mic. You can unmute yourself and ask your question.
Thanks, Ashley. Thanks, Reginald and Rudolph, for an excellent presentation. Rudolph, could you just, although this is an introductory course, can you just share with our colleagues how condition assessment has virtually ballooned in the hydropower industry for plants that are 40, 50, 60 years old, and how you virtually have to throw quite a big multidisciplinary team into doing that. Thank you.
Thank you for the question, Alan. Yes, well, as Reg have indicated, hydropower plants can last for years. The example that I showed you, Nalubali hydropower plant, Uganda, was actually constructed in the 1950s. And there are a number of them across Africa, and actually there's a lot more, obviously, in Europe and in the States, etc. So these plants are still, I mean, the hydromechanical, electromechanical equipment is refurbished typically in a 25 to 30-year cycle, depending on the specific plant and the conditions of the plant. But the actual civil infrastructure lasts forever. But there are problems such as ASR at some of these plants, normal structural cracks that starts developing for various reasons, and then you need to fix up those plants. It's actually quite expensive to reconstruct the plant from scratch, specifically on the larger rivers, etc., such as the White Nile, well, any plant for that matter. And it is cheaper to just recondition that plant. So it's basically because hydropower plants can last for that long, and you can over a period of time replace the hydromechanical, electromechanical equipment, but at a certain point in time, the civil infrastructure needs to be looked at as well, and then you start doing major upgrades to them. Thank you, Alan.
Thanks very much. Thanks for the opportunity, Ashley.
All right, thank you. If there are any other questions, I don't see anything in the chat. If you have some comments or questions, you're welcome to raise your hand. All right. Nasatane, you can unmute yourself and ask your question.
Oh, thanks. Thanks, Ashley. I'm Ditatane Madidam from Lesotho Highlands. So I'm interested on the equation, the basic equation that Reggie did touch on. I'm just interested the head losses. How far does it extend? Does it stop right at the turbine entry, or also even the exit? The head losses. That's my question. Thanks.
Okay, now thanks for the question, Tani. So the short answer is you look at all the head losses in the control volume or the boundary where you're taking your gross head. So if you take your total gross head from the upper reservoir water level to the downstream river water level, then you have to look at all the losses between those 2 points, because those are the total losses that you then have to subtract from the available gross head. Does that answer the question?
Yeah. I think you did touch, yes. But the main question, what I was asking is the losses after the turbines towards the tail race. Do they matter on the rating of the turbine?
Yeah. So if you take the level, as I said, to the downstream tail race water level, then you have to also account for the losses between the turbine and the tail race, because all of that forms part of the hydraulic grade line. So if you draw a hydraulic grade line and energy grade line, then you draw it essentially up to the tail race, and that means you have to account for the losses that occur between the turbine and the tail race itself.
Right. Okay, thanks.
Sorry, I'd just like to add, obviously you have a Pelton, it's up to the Pelton intake, because the Pelton, you calculate the head based on what's at the Pelton. But the head loss, because Pelton is typically 300 meters and higher, the bit of loss of head loss from there to the river is very small in comparison.
Maybe to add to Rolf's response there, thanks for that, is with the Pelton, you've got a free discharge. So the water hits the buckets on the Pelton runner, and then after it's gone through the buckets, turn the bucket, the water has got a free discharge. Whereas with Francis and Kaplan, you've got a submerged draft tube or, on the tail race side. So that's why with a Pelton, you only go up to the nozzle at the Pelton. Thanks, Rudolf. You're on mute, Ashley.
Oh, sorry. Simo, you can unmute yourself and ask your question.
Thanks to Rudolf and Reginald for the presentation. I think my question is more on the investment, because now looking at the infrastructure, it's a very massive infrastructure. So who does normally do the investment? Who do invest? It government institution or normally it's, the private organizations? Is it something that can be adopted to South Africa? Because I see most of them, they are on the other countries in Africa. So can we do this thing in South Africa, especially looking at the pump hydro power infrastructure? It's a massive infrastructure and it should be quite expensive for construction. And now in terms of investments, who do normally do the investments on such projects?
I'll take that question. Thanks for the question. Well, it depends on who has the appetite and who wants to develop. Sometimes there are utilities. So Eskom is currently considering constructing a pump storage scheme. So that's obviously government-based, and typically then there is funding available from something like an international funding organization for that. That will then fund it, but that has to go then through a proper rigorous process. But there are also private developers in South Africa currently looking at pump storage schemes also to develop it, and also private developers looking at putting in hydropower infrastructure on existing DWS infrastructure as well as other places. So where it makes sense. Obviously, seasonality is quite a key problem. But for instance, there are a number of sites across South Africa where there are a lot of infrastructure available, and you just need to add on the hydropower plant to benefit of the actual outflow from the dam. Typically, it's at a dam, but there's also some high pressure systems that the energy is actually wasted by energy dissipating valves, where you can actually replace that with a turbine as well. But to answer your question, it depends on the client. So sometimes it's utility and sometimes it's the investor. And what you do throughout the design of the hydropower plant is looking at all the options, and you're looking at the LCOE type of calculation on all the different options, trying to optimize to understand what is the best costing option for when you design the plant. So the size of the plant, the number of turbines, etc. All of those things you start analyzing at a low level, and then all that cost rolls up into a total financial economic model, and then that is actually analyzed for various options, typically at feasibility study stage, and then that goes into a financial model to determine if I sell my electricity at 6 cents per kilowatt, or I'm talking US cents now, or 70 cents, this plant becomes viable, and then you start figuring it out from there.
Right.
That answers the question. It's actually quite a loaded question because it's actually quite a complicated process.
No, it does sort of answer it, Rudolf. Thanks.
Sim, if I can maybe add there, if you're a private developer and you've got an off-taker, if you've got someone willing to buy the power at the right price, then as a private developer you can develop a pump storage or a run-of-river hydro scheme. And so it's all about what does it cost you to build, and can you sell that power at an appropriate rate for an appropriate time to recover your cost.
Yeah, thanks, Reg.
Okay, we have a question in the chat. It's from Mizamo. She's asking, is AI currently used in hydropower plants? If not, are there any plans to integrate AI in hydropower plants, and would the integration be necessary or feasible?
See, Rudolph, video is lagging, so I'll start with the response if he wants to add. Yeah, so all the turbine manufacturers are already using a turbine generator, key equipment manufacturers, they are using AI in improving their designs to make their equipment more efficient.
I sent you the technical list. You can track it.
Sorry, Rudolph, we're struggling to hear you. Reginald, you were on mute. So if you want to continue the question.
Okay, maybe let's get Rudolph's video turned off in case there's a bandwidth issue. Yeah, but to answer the question, we're definitely seeing it coming through on the manufacturing and design side. Certainly,
To add on, let's
see if we can.
I'm just going to mute him for now, then you can finish up answering the question.
Okay, good. No
All
problem.
right, there we go.
Must be struggling. Okay, so yeah, so the answer to the question, yes, as I think in any industry around the world, AI, everybody is asking how can AI assist us and what can we do and how can it save costs, etc. In the hydropower space, we're definitely seeing it on the equipment side. It's coming through on the design as well, to automate and improve designs. So I think it's a bit of a slow start maybe, but they are in major hydropower facilities. We already was at a conference, Africa Hydropower Conference earlier this year, and there were actually many presentations done already on AI and the use of AI in asset management. So not just in the design and initial construction, but also in how you can use AI to improve the management of that asset. So in your operation and maintenance phase. So yeah, there's some very interesting work being done across the world on that, and I think it will definitely become a much bigger player in the hydro field as well, across all phases, from development through to construction and commissioning.
Okay, thank you so much. I'm going to take that as the end of our questions and answer session, since we don't have any more burning questions at this time. I would also just like to thank Rudolph and Reginald for taking the time to come and do this presentation for us. And thank you for everyone who joined today. Really hope that this session has given you a stronger appreciation for the foundations and principles of hydropower, as well as the importance of water energy systems in the context of Africa's sustainable future. So on behalf of the SANCOLD YPF, we encourage you to stay engaged, continue expanding your technical knowledge, and make the most of the upcoming opportunities for professional development that we will be hosting. So on that note, if you'd like to be part of SANCOLD, you can go to the website that is displayed on the screen right now, and you can become a member just by clicking on the Become a Member button and following the steps. We have our annual conference coming up from the 5th to the 6th of November, and this will be held in Gauteng, and any more information that you require on that will either be on our LinkedIn page or on the SANCOLD website. Our LinkedIn page is a good place to start if you want to find out more about our webinars, and if you want to catch up on anything you've missed so far. It's a great way to stay in touch with our community, so you can go and follow us over there. Then, like I mentioned, the conference is coming up, and also look out for the hydropower training course from the 3rd to the 4th of November at Sutari's offices. You can look at the website to see what the costs and benefits for either attending online or in person, if you want to expand your knowledge on hydropower. Thank you so much for today, and I'll see you at the next webinar.
Thank you, Ashley. Appreciate it.